And thanks, General, for organizing the masterclass here. It's really a pleasure to be back in Copenhagen, and also, yeah, nice to be able to present something here. As I said, or as Peter said, the title of my talk is Free Factor Complexes as Boundary Structures. And what I will talk about today is, yeah, all based on joint work with Radhika Gupta, and well, mainly an article, I guess, completely an article that was in the end published last year. Before I come to free factor complexes and their relations with boundaries of outer space, let me give you a bit of an overview what we saw this week. So I hope you can see the left-hand side also on Zoom now. I mean, you can't see the board yet because I didn't put it up, but I think now you should be able to see this board, right? Okay. So what did we see this week? There's at least a bit of what we saw. We saw different types of groups, and the main examples were, say, three families. Namely, we had SLNZ, or also SP2NZ, which I'll put in the same corner around here. We saw the mapping class group of a surface, okay, let's say without boundaries here. And we saw out of N, the outer automorphism group of the free group, or also out of N, but in my talk, I'll focus on out. Then we saw associated moduli spaces to these. So for SLNZ, we saw symmetric spaces. We had Teichmuller space in Tara's talk, for example, mainly showing up. And we had outer space in Kai-Uwe's talk that was introduced. Then we saw some boundary structures of these spaces and some descriptions of those. Namely, what we saw in Mikola's talk was that by work of Boyle-Sea, we can basically identify a boundary in a suitable way of symmetric space with a Tietz building. And in Tara's talk, we also saw that the boundary of Teichmuller space, now in the case of Harvey boardification, can be seen, has another kind of description. I'll be a bit vague here for the moment, but it can be seen as the curve complex. And we also saw that these complexes in the first two cases are homotopically at the boundary quite nice. So we saw in the somewhat interior, the moduli spaces here were all contractible. And the boundaries were, well, at least in the first two cases, spherical. So we saw the Tietz building, now this is associated to SLNZ, was homotopy equivalent to wedge of n-2 spheres. The curve complex for closed surface was homotopy equivalent to wedge of 2g-2 spheres. And what I will talk about today is the somehow missing corner here in the picture. So there are two main things I want to talk about. Namely, I want to start with outer space, give you a certain description of the boundary. I'll be a bit more precise what I mean with certain description. And then I will talk about how one can use this description to show connectivity properties, say, for the boundary. Yeah, we won't get an as complete answer as in the two cases above, but this is at least the aim of what I want to do, the corner down here. Okay, and for my talk, well, I guess I need to stay here if you want to see me for the moment. For my talk, basically there are three parts. I'll firstly talk about what I mean with boundary of outer space in the setting here today. Then I will tell you what an equivalent description of the boundary can be, and in which sense it is similar to the descriptions we saw above here. And then the last part will be to talk about connectivity properties of this boundary structure. Okay, so let me, thanks. Let me start with the simplicial boundary, or the boundary of outer space. Take my chalk with me here. And for that, actually, I'll start at the board over here. That should be board 2. Yeah, where I recall a bit the definitions from Kai-Uwe's definition. So that's somehow first part now. First part is simplicial boundary of outer space. I'll write outer space as CVN here. So let me recall what we saw in Kai-Uwe's lecture about outer space. We saw that outer space is a moduli space of marked graphs And here's a small part of it. Maybe focus on that triangle here in the middle. The points in this space are graphs and that have fundamental group Fn. Better like this? I don't know. I mean, maybe people on Zoom can say whether it's better now.
This sounds better.
Okay, yeah, then I'll keep it like this.
Just a very high pitch.
Okay, yeah. I mean, I can also move it further away if that. Okay.
No, the other
Okay,
way. The other way there were interferences.
Okay. Yeah, then I hope it's better now. Please tell me if there's another problem with it. Okay, right. So the points here in outer space, this is CV2 that I'm drawing here, were marked metric graphs, and marked meant that there was an identification of their fundamental group with a standard copy of the free group on n generators, and that amounted in giving a homotopy equivalence between the rows here with 2 petals and the graphs in the middle. And I drew exactly the same picture that you saw in Kai-Uwe's talk about this part. One difference in this talk in comparison to the talk of Kai-Uwe is that in this talk, I will talk about unreduced outer space. And unreduced here means that what I will allow are graphs with separating edges, namely graphs that look, for example, like this. Kai-Uwe didn't allow this in his talk. He said, well, if you have an edge like this, such that if you delete the edge, there are 2 components to the graph, then this is not a point in outer space. I will allow it here. This leads to differences definitely in the spaces, but the unreduced or the reduced version that Kai-Uwe talked about is a deformation retract of the unreduced version here. And I will maybe talk about the differences in the end of the talk, but here I will use the same notation CVN, but now also allow these separating edges. That means that also in CV2, we get another type of triangles. So this was one triangle corresponding in the middle here, a simplex corresponding to this graph with 3 edges. Now we have another type of graphs with 3 edges that can occur for F2, namely this handle body, well, this type of dumbbell graph that it shows up there. Yeah, and okay, this would also get a marking of the rows. I didn't draw it over here. Okay, now, okay, we saw that in Kai-Uwe's talk that outer space is a union of simplices, but not all boundaries of simplices were actually part of the space. So let me draw this in that picture. We saw some, so this open simplex, for example, is completely there. If you walk around in this open simplex, we vary the lengths of the different edges of this graph. If we go to this edge here, one of the edges of the graph has actually gotten length 0, then we are at a face of smaller dimension. But now, if we wanted to go to this point over here, what would happen is that we would obtain a graph where we have 2 edges collapsed. So we would have something like maybe this graph with only 1 loop, and this was not a point in outer space because its fundamental group is not F2. And this led to certain faces here missing in the picture, namely all the vertices of this pink triangle that we see, well, of this big triangle. And then here it's actually similar. Here's another face of dimension 3, a triangle corresponding to this dumbbell graph, but some of its faces are missing. Namely, if I collapse one edge here in the middle, separating one, then I get to this edge of outer space, which is fine, it's in there. But if I collapse one of the other 2 edges, I will actually collapse a loop and we'll get something that is in the boundary of outer space. Yeah, so here this would correspond to, say, a graph that looks like this. I'm not sure whether I drew it now the right way around. And here maybe a graph that looks like this. And both are a priori not points in outer space. Okay, up here, something like this. Still a graph, but not points in outer space. And exactly the pink things that I drew in here is now what I will call the simplicial boundary of outer space, in this case, CV2. And those are exactly the points that I want to add to the space here. I want to add all faces of simplices that are there in outer space.
You said the unreduced outer space is homotopy equivalent to the reduced one, but not the
Yes.
boundary. Is that correct? You
That
have
is
just
correct.
made it connected where it wasn't.
Yes, that is definitely correct. I'll maybe at the end of the talk I'll say something about that. There's definitely a boundary in that, difference in the boundaries. Okay. Okay, so I will I'll write something about the definition, but I will stay a bit vague. The best thing maybe to keep in mind is this picture. I add all the faces of simplices, but well, to give a bit more of a rough idea, what I will use now is I'll consider outer space together with its boundary as then I'll just write vaguely in words the moduli space of marked metric graphs. Where and now one possibility to write this is that now I allow subgraphs to have length 0. Yeah, so instead of saying I collapse this vertex, I just say it's still a loop, but it has length 0. This was not allowed in Kai-Uwe's talk, but I will allow it now for this space together with the boundary. And then, okay, modulo all subgraphs of length 0 are identified with one another. There are different ways to actually formalize this, and one that is maybe that I will also now only vaguely
quick
define.
question.
Yeah.
So in particular, you really just add a point, and unlike Kai-Uwe who added a
Yes.
line there.
I really only add a point at this point. Yeah, that is true. So I will not cut it off like this. Well, Kai-Uwe said, cut off, shave off this part somehow. I will add the point instead. Okay. So one way of making it a bit more formal is to say that the points now in outer space together with its boundaries are marked metric graphs of groups instead of just taking graphs of groups. And if you don't know what exactly that means, that's not too bad for this talk. Just think of the graphs as being equipped with additional information of a subgroup that you attach to every vertex. Yeah, so for example, when we go from here to there, we had a marking here. We identified the fundamental group of this graph with the fundamental group of this object. Now, when we collapse, say what is collapsed? The orange, I think, over here. No, the blue is collapsed. When we go like here, what we imagine is that the graph still has fundamental group this. The loop somehow has this fundamental group, but now the loop, the blue loop over here is somehow stored inside the vertex. Somehow we get a copy of Z now inside the vertex. Just some extra decoration yet. Yeah. Yes, so what you would get in the boundary, yeah, this is additional. The question was, is it similar to remembering the genus? And yes, this is somehow similar to what Søren talked about today, if you want. The underlying graphs that you get in the boundary are stable graphs. You could add a weight as the sense of what is the rank of the fundamental group of the subgraph you collapsed. But here we get a bit additional information because this point also has a specifically subgroup of F2 that it's identified with. So this is the additional marking somehow.
So it's not just Z, it's an embedding of Z into F2.
It is specifically the so it is
like it's
the fundamental group
generated by
this
X1
loop seen as a subgroup of the fundamental group of this. Yeah, that would be the more precise statement. I mean, it's admittedly a bit vague here, but I want to save a bit of time too. But I guess that is at least the idea. No. Okay. Yes, that is true. So the question was what the action of out of n on this space does, and it will not be by finite stabilizers. So this was a bit Kai-Uwe's point where he said, well, why don't we just add these points at infinity? The problem is we now get a space that still out of n acts on, but the stabilizers will not be finite. For example, this point, this thing here will definitely well, okay, that's a bit hard to say, but everything that, okay, no, I won't phrase it more precisely, but yes, there will be non-trivial stabilizers. Yeah, the stabilizer is not a copy of Z, right? It's, I mean, not F2 acting. It's the outer automorphism group. But if you have an automorphism that's of the free groups that stabilizes this free factor up to conjugacy, yeah. So you can phrase it like this, but it's out acting, not F2. Okay. Now this is one way to describe the boundary, but what I will actually be working with is that the following description of this space, namely it can be described as the geometric realization of a certain poset that I write as FSN. And FSN is the poset of free splittings of Fn. No, yeah. Thanks. Yeah. Poset of free splittings. Of Fn. So yeah, one way to say this is this would be a poset of marked graphs of groups together, and the order relation would be given by collapse of subgraphs. Okay, so marked graphs of groups, I mean not marked metric graphs of groups, that's somewhat my point. The poset you would see over here would be, you add 1 point for each combinatorial type of graph you see in the picture. One here, one here, say, here, 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 here. Yeah, those are all the combinatorial types of graphs I see in the picture. And the geometric realization of this poset would look like this. Oh, sorry, this was not correct. Okay, well, okay, now every edge should be there. So what I'm saying is this is smaller than that, because if we collapse an edge in this graph, we obtain this graph. Similarly, this is smaller than both of these because we can collapse the subgraphs in here and end up at this point there. Yeah, but now we got a more combinatorial description of this space, and instead of studying this space continuously, I will study the poset from now on of free splittings. Now we have this, I drew in the geometric description, say I drew the boundary and the interior of the space. Something similar I can also do in terms of the posets. Namely, what I can do is I can write this poset of free splittings as a union of two subposets. The one being Ln, I'll say what it is in a minute, and the other being what I will call Fsn infinity. And now in this notation, Ln is the spine of outer space. So this is something that also showed up in K-Uwe's talk. Those would be, I'll just write it, all elements in the free splitting complex such that every vertex group is trivial. Yeah, with vertex group, I mean the decorational group that we added to the vertices. So for example, this point has, well, no decoration group, so I'll say it has a trivial vertex group. This was called Kn in Kai-Uwe's talk because there it was the spine of reduced outer space and not unreduced. Here it's called Ln. But again, this is a Kn is a deformation retract of this space. And then there is the second part, the boundary. This is Fs infinity. This is, okay, to save myself some time, I'll just say it's the complement of that. So those are all free splittings here that have at least one non-trivial vertex group. Should I write a bit bigger? Ln Fs, yes, I see now where it is, yeah, sorry. N infinity over here sorry, let me say it again. The boundary of this space, the points at infinity, so somehow the analog, if you want, of the A infinity in Terrace talk, is given by free splittings minus those that lie in L. So all free splittings where that is at least one vertex group that is non-trivial. Right, and this is so this is what I will talk about in the talk. These are basically the objects we need. We'll have this free splitting complex. We'll have in it an interior poset that is Ln, and we have a poset at the boundary that is Fs infinity here. And this decomposition here is in terms of the posets, not in terms of the spaces, right? Because the pink thing, for example, here, maybe I can add that. The pink thing here is the geometric realization of Fsn infinity, or the part of it that you see in this picture. But the spine is not everything yellow inside. Yeah, it's just consists of this point, this point, this point. So it's a subspace of the yellow thing we see in there.
So that seems not to be true. You also have things connecting these two, right? So
this is why this is a decomposition in posets and not on terms of geometric realization. Yeah, maybe this is something I should stress.
as poset, okay.
This is really, if I write, I will try to make it clear and write geometric realization at least, well, okay, at least mostly I will write geometric realizations. So basically always here, when I talk about this, it will be posets. This is really just a poset of something. It's a discrete object, and only when you apply geometric realization, you get a space. So maybe to make it a bit clearer, this is the subposet realization of L2 in this case. The realization of this subposet. And it is not true that as a space, it's the union of these two posets, but as a poset it is. Yeah, the rest is then more only technicalities. Okay, so this was the space part. I now go next to the middle board. People here will still have the picture over here, but I don't know, maybe for people on Zoom, it might be helpful to take a screenshot now if they want to if they want to have this picture by the side, that might be helpful. So I'll walk over and give you some seconds to take a screenshot if you want. Okay, I hope that worked, and now I'll go on with the second part. And the second part are the free factor complexes. So let me just continue down here. Free factor complexes at infinity. Now, okay, what I said in the beginning of the talk. Yes.
So when you have two posets, one of them is below the other. Isn't it? They are not intertwined.
Heard two things at the same time and didn't understand one of them.
Caillou, sorry, I'm sure you heard yourself, so I'm going to mute us while you talk, okay?
Okay. So you have this poset decomposition into two parts, and they are not interleaved, right? They are just, one is strictly below the other.
They are disjoint, if you want, if that is what you want to say. The spine is disjoint from the boundary.
No, it's more, right? Everything in the boundary is below.
Yeah, right.
Right.
Right. It is true that every point in the spine, no point in the boundary will be greater than something in the spine. This is also true.
Yeah. Thank you.
Actually, maybe let me just shortly come to the table I had over here. So to roughly say what I want to have now. Now I have some kind of description of the boundary, but well, for me, why is it not nice enough? Say we have a description now in terms of these splittings, and the reason is I want to have a description that's a bit more like these descriptions over here. Let me shortly recall what these were. The Tits building now for SLN was a set of or a poset of subspaces of Q to the n, or I'll write set to the n. Yeah, those are not subspaces but direct summons, but okay, just for the analogy, I'll write like this now. the curve complex that was somehow, if you want, a poset of systems of curves on the associated surface. So why could these descriptions be somehow more, somehow better than just saying it's a boundary of these spaces? I think the underlying reason is a bit that one way to consider these groups is as automorphism groups of other structures. So the most natural object, I guess, that SLN actually acts on is set to the n, right? These are matrices. I mean, that's the natural thing that SLN acts on. The natural thing that, okay, mod G acts on is, well, mod G is also basically the outer automorphism group of the fundamental group of the surface. So somehow the natural thing here to act on is the fundamental group of the surface. And this is a bit reflected in the structures we have over here, yeah? This is a somehow subgroup structure, if you want, of the thing that this group acts on. This is a kind of subgroup structure or sub-element structure, yeah? If you have curves, if you have a curve on the surface, that's an element in the fundamental group. So somehow the action here of the mapping class group on this complex is quite natural in the sense that it actually acts on the underlying group. I want some kind of similar description now for this. Now, what's the most natural thing that this group acts on? It's Fn. Yeah, I mean, this is the natural thing that this object acts on, or conjugacy class of things in Fn, probably I should say. Now I want to have a description of this complex of this boundary that works with this group description that we have. This is the next thing I would like to talk about. So what would be possible analogs? I will tell you about two candidates for such analogs. For this, I need to do some definitions. So the first is, well, a free factor. I shortened that a bit. A free factor we already saw in Jeremy's talk. Yeah, a subgroup of Fn is a free factor if, well, Fn decomposed as a free product like this. If there is some B such that this is a decomposition. Now the free factor complex was already defined in Jeremy's talk, but I will use a slightly different version. I'll write it as this Fn. And for me, it will be the poset of conjugacy classes of free factors in Fn. And the reason I'm talking about conjugacy classes here and not just free factors as Jeremy did in his talk is that I want an action of out of n on this object. Yeah, that's the difference, but I mean, it actually makes a difference for the space, but for the rough picture, I guess it's basically the same definition. So this is one space we already saw, one complex. Now there is another thing that I would like to talk about that is also maybe a reasonable candidate. And this definition now is due to, well, maybe let me just put it on the new board. This definition is here, is due to Handel and Moshe. And it's the following complex. So firstly, I will say that a free factor system in Fn is a collection of, maybe I'll write like this, A consisting of A1 until AK of conjugacy classes of free factors such that after choosing suitable conjugates, the free group decomposes as a free product over all these AI together with possibly trivial rest B. So some are compatible free factors. That's very similar to this partial basis complex, I guess that. It's smaller, that the zoom is, okay, I read larger now. Okay, now how do we make this will be the vertices of our complex, or equivalently the elements of the poset. Now I want to write a partial order of such three factor systems. And I will define it as follows. For three factor systems, I'll write FFS, A and A prime. We'll say that A is smaller than or equal to A prime if the following holds true. If, okay, and now the condition is for every component, so for every such conjugacy class of three factor in A, there is some component in A prime such that after choosing suitable conjugates, AI is contained in a J prime. And now this defines a posset. I'll give an example in a moment. This defines a posset structure on the set of all three factor systems in Fn. And the resulting posset, or I'll write the complex of three factor systems sorry, I want to write a bit bigger, right? Of three factor systems. And I will write this as Fn is the poset of all, is the associated poset, I'll just write. Yeah, so the elements are exactly these three factor systems. And the order relation is given by what I defined over here. No, I mean, I start writing bigger only here. Yeah, sorry. I can do it now. And the next line you'll see it. It will actually become bigger. So an example, in F3, we would have a chain like this of three. So let's say we have this generated by A, B, and C. Then, for example, this is a three factor system. The conjugacy class of, now I have to add many brackets. It's a set of two things. Both are conjugacy classes. One is of the subgroup generated by A, one is of the subgroup generated by B. And this is smaller, for example, than the three factor system that looks like this. Maybe the subgroup generated by A and B. And this again is also smaller than, for example, this. The same element plus the subgroup generated by C. These are all three factor systems that we would get. And this is a part of this order that we see. So if one goes a bit through the dimensions, then one realizes that the dimension of this complex is 2n minus 3. Yeah, I mean, one needs to think shortly about it, but it's not hard to show. And the second thing is that also the three factor complex is contained in this complex of three factor systems. Namely, we can just take the three factor systems that only have one component, for example, such a thing. This is the same as a conjugacy class of a three factor. And the order relation on this sub-poset here is exactly the same that we defined above for the three factor complex. Okay.
I'm sorry, maybe I misunderstood how that works. Can't you just have at most n many free factors and then the dimension would be n minus 1? I'm not.
Yeah, but you see, for example, this inclusion here.
It's also the inclusions.
Yes.
Yeah. I see.
Okay, yeah. So now I got some complex of three factors and I want to relate them to the boundary, to the description I had in the first part. How can I do that? Well, I know now for these points in the boundary of outer space in this FSN infinity, those were free splittings with non-trivial vertex groups. So what I want to do is I want to define a poset map from FSN infinity to the complex of free factor systems. What I need to do is I take such a splitting, and now I need to associate to it a free factor system. The question is, how do I get this from? And well, now I claim that for every such free splitting, the collection of all non-trivial vertex groups is actually a free factor system. Non-trivial vertex groups. So why is that? Well, the only thing I'm using basically is that how does a vertex group here arise? It arises as the fundamental group of a subgraph that has length 0. But it is true that whenever you have a graph and then the fundamental group of a subgroup of the subgraph is a free factor in the fundamental group of the ambient graph. Yeah, this is just true because it's a one-dimensional space and well, not so much else can happen. Yeah, I can repeat it.
How do you treat base points so yes, how do you treat
how do I treat
base points and this
Yep.
conjugacy?
This is exactly the point. I do not treat base points at all, and this is why I have to put conjugacy classes everywhere. Also, this identification, okay, now online people can't see, but the identification that we had for the space was only identifying things with conjugacy classes, yeah? Because we never specified a base point. I mean, these were not pointed homotopy equivalences between the rows and the graphs in the middle. Those were just homotopy equivalences. So everything is only specified up to inner automorphisms, up to conjugation. Okay. Okay, and I'll just claim, I won't say that now, that this relation is compatible with the poset structure on both things. Yeah, I guess you have to believe me for that for now. Yeah. So this gives us a map between these two posets that relates the two. So that gives us a relation between some kind of boundary structure of outer space and some kind of more internal group structure of the free group. This free complex of free factor systems over here. And now the result of Radhika and myself is that the map F is a homotopy equivalence. Well, I'll write in two parts maybe. First part, F is a homotopy equivalence. And second part, F also restricts to a homotopy equivalence. From FS1n, I'll define it in a moment, to the free factor complex. Yeah, and now FS1n is a subset of this boundary of the free splitting complex. Namely, those are all elements, all free splittings, where S has exactly one non-trivial vertex group. Yeah, the boundary consisted of graphs that have potentially more non-trivial vertex groups. There is a subposet where you have exactly one vertex with non-trivial vertex group. And the map F restricts, that's easy to see, to a poset map from here to there, but it's also a homotopy equivalence on these posets. So what I'm saying is the entire boundary of outer space that we saw in this description of the free splitting complex is homotopy equivalent to this complex of free factor systems, whereas the subcomplex here, consisting of things with only one non-trivial vertex group, is homotopy equivalent to the free factor complex. Maybe I'll.
Now I have a question.
Yes.
You want to change the camera?
Yeah, but I mean, you can also ask the question first. I want to show it in the picture where the parts here
yeah,
are.
well, that's related too. So I'm first of all, I'm thinking you're never gonna hit with the first map. You're never gonna hit anything where you have a complete factor decomposition.
Yeah, okay, maybe I'll go to the
yeah.
picture, explain two things, and then should be clear.
All right. But isn't it then even like if you out of FFN you don't allow a complete factor?
No, you okay? You actually hit those systems.
Oh,
This
you
is
do?
the
Okay.
misconception, and
Okay,
maybe I should
then-
make that clear.
Yeah, please do.
Okay, let's look only at this part. In this part, we had a graph. Now, how do I mark that? I'll now circle around everything that is in. So everything where I put a circle, this is in FS1N. So those are the graphs where we have only one non-trivial vertex group. There is this point over here, this point over here, and this point over here, and this over here. Yes, and the one up there. Here you always get exactly one vertex with non-trivial vertex group. This point, this, maybe I'll draw it thickly to make clear that there is some decoration to it. Well, the same for the others. Here we even had the decoration. This, however, is not in the post-set. And what happens here? Well, what happened here is, now the coloring might not agree 100% with the marking that I drew there. But what happened is that this is a graph that has no fundamental group by itself. However, it has two vertices that are both decorated with a copy of Z. So this is the image of that under the post-set map that I described there is a complete factorization of the free group. Yeah, there's no pi1 left in the graph and everything is stuck in the vertex groups. So does that answer your question, Peter?
I don't think it does. Wait, sorry.
I think this is the point where you should maybe have a look at.
Sorry, yes.
Yeah. And this is also what makes the difference here between the reduced and unreduced part.
Okay, thanks. Yes.
Yes.
Benjamin, is this subspace connected?
What subspace?
This with the one decoration.
With the one decoration.
Yeah.
Yes, and this is because, yeah, okay, that will be probably, okay, I'll show you now in the next section why or give you an idea of why the free factor complex is always a wedge of n-2 spheres. So in that case, the wedge of 0 spheres, so here it's not connected.
Okay.
Okay, maybe other further question on the post-set map here? Because otherwise I would, yeah.
So do you expect this map F to be a local equivalence? You see in point 2, this FS1N is precisely the preimage of Fn under the map F, isn't it?
Yes, that is true.
So one could ask if for every subposet of FFN, the map from the preimage of that subposet to the subposet is an equivalence. For instance, because fibers of F are contractible or something like.
Yes, okay, I don't know. Maybe I should just say, I don't know. Maybe we can also talk about it later, but
Yes.
I think maybe that brings us a bit away from the main topics. Okay, but then let me just mention, okay, I won't write anything more specific about it here, but the reason that this map actually is a homotopy equivalence is just the fibers are contractible. Yeah, this is a bit cheated, but I mean, this is somehow a bit of work definitely here to do as well. I mean, usually I would also state this as a theorem because the fibers that we have are relative versions of the free splitting complex. The free splitting the fibers are relative free splitting complexes. I'll just say relative versions of FSN. FSN itself is contractible. That's a result by Hatcher. And yeah, we then and are contractible. And then we show that this is also the case for this relative versions. Yes, there's definitely some, well, quite some work to be done here, but I won't talk about this now. Okay, and then you use equivalence, well, equivalent post-set lemma again, as we already saw in the talks of Robin, and also in Jenny's talk, we definitely also saw it. Okay. But maybe instead of telling you more about why this is a homotopy equivalence, I would like to also come to a third point, namely, as I told you, that I also wanted to talk about the connectivity properties of this boundary, or the homotopy types, maybe. So last section, connectivity of those two complexes. Okay, I need, so yeah, the aim is the last part of this table, the bottom row thing. What is the homotopy type of this boundary stuff? I need one definition before I can write that, namely a core subgraph. Oh, sorry, a bit bigger, of a graph G is a subgraph that is, well, I guess, no, okay, it's similar to the stable ones in Søren's talk, but I'll define it new here. Of it's a subgraph that has such that, okay, such that the fundamental group is a subgraph H, such that the fundamental group of every connected component is non-trivial. And such that every vertex is valence at least 3. Example, take G to be this graph, then for example, this is a core subgraph, the union of the two things. Yeah, I allow disconnected ones. Whereas, for example, this is not. Yeah, because here there's something that has valence less than 3 in the subgraph.
So you always allow a loop with one point that also doesn't have valence 3, but you always allow that, right?
Oh,
I mean, that's
no,
necessary
sorry,
to have a rows
sorry,
anyway.
I should have, no, his valence at least 2. Sorry. Yeah, okay, sorry, you're right. That was a bad, yeah, that was just a, yeah, I confused the definitions there. No,
But
his valence at
then you
least
would
2.
allow the other color as well.
No, because here, this has valence 1 in the subgraph. This vertex has only one edge.
Oh,
coming out from it.
I didn't see. I thought it was going around that way as well.
No.
So you allow valence 2 now.
Only valence 2, sorry. Yeah, that was just a mistake. Okay, and now, yeah, for the last minutes, very short idea of how can we use this to get connectivity properties of the boundary. Okay. So I will first define, I will only do it now for FFN, not for FN itself. So I'll define Z as the following subposet of the product of these two posets. Namely, it is given by all points G comma S in the product such that S is obtained by collapsing a core subgraph of G. Yes, this is more or less the same, but I also assume that the thing you collapse is a core subgraph. But that is more for technical reasons. It doesn't matter too much, actually. Otherwise, would only get a bit blown up. Right. So in particular, S is smaller than G with the order relation that I wrote down there. But it says a bit more. You need to collapse a core subgraph to get there. So basically, I want to study this boundary, and what I have here is a bit of a thickened up version. I added to every point at infinity, I added everything in the interior that collapses to this thing at infinity. And somehow about a neighborhood, if you want, of every point at infinity. Now there are projection maps to the two factors. And you can show the following lemmas. The map P1, no, sorry, I start with P2 is a homotopy equivalence. I won't say how this is proved now, but this just says that this thickened up version, actually thickening up didn't really change the homotopy type of the boundary. Yeah, it's really just a thicker version, but we can collapse again and get the same thing here. This is just thicker. So basically, this is still the same thing that we have over here, except that we have this additional structure. So the only thing we gained now is to get this projection map to L. And this is what I want to use in the following lemma. For all G in L in the spine, I claim the fiber P inverse of L bigger equal to G. So everything in Z that maps to something that is bigger than G. So I think in Jenny's talk that was L in P1. I think she wrote like this: everything, yeah, the pre-image of everything that's bigger than G under this map. I claim that this is always n-3 connected. And I would like to give you very shortly an idea of what one needs to understand for showing this. Namely, what do the fibers here look like? Let's just consider the inverse of G, yeah, to make things a bit simpler. What is the pre-image of a graph G? Yeah, those are all pairs in this poset of tuples G comma S. The G is always the same. Now, so that is the same as the set of all S in Fs and infinity, such that S collapses to G, or sorry, G collapses to Fs. By collapsing core subgraph. And this is now, instead of looking the things I get when I collapse core subgraphs, I can equivalently just look at the set of all core subgraphs and study what they look like. So this is basically the same as the poset of all proper core subgraphs of G. Proper core subgraphs of G, together with the inclusion relation. Yeah, one needs to check some things on the way here, that everything is compatible with the order relations that I defined. These are the results of collapsing the core subgraphs. I say that this is isomorphic to the poset of just taking the core subgraphs. And my important point is this is actually for every G a finite poset, because G is really it has an underlying graph that is a finite graph. It has finitely many core subgraphs. So the only thing one needs to show here is that for all G, this finite poset here is highly connected. And that is the case. Yeah, one needs to do some combinatorics of graphs, look at subgraphs of the graph that have certain constellations towards one another. One can show that this is the case, that this is always n-3 connected, this finite poset. It's contractible exactly if there is a separating edge. And otherwise it's a wedge of spheres. Yes. Actually, I mean, we didn't do everything on our own here somehow. So I mean, okay, proof is somehow by Radhika and myself if you want, but this builds on, so Karen Volkmann has a paper on trees in graphs, and this is very related, except for, I mean, yeah, I won't say too much about that, but I mean, there are similar postsets of graphs that are already studied, and you can use that. Yeah. This is exactly where I use the core subgraphs. Well, I mean, I defined, yes, the question was, I think, where the core subgraphs here play a role. Okay, I mean, also in lemma 1, I used core subgraphs because I only, but talking about this core subgraph is more, so I'm claiming the whole thing also works if you do not take core subgraphs, then just your subgraph posets get a bit bigger. It's really just for technical convenience to consider the core subgraphs, because every subgraph has a unique core subgraph. This is what you need to use. And the posets deformation retract to one another. So let me just say, so this is actually this is basically the exercise I gave on the exercise sheet. And so to look at this poset of core subgraphs of a certain graph, and I think it's a very good exercise because you only look at finite subsets of graphs in a graph, but what you actually study is the boundary of outer space around a certain vertex. So yeah, this is in the exercise that I put on the sheet. Now, let me get back to how this helps us here. So we now know that all these fibers are highly connected. This implies, by again version of Quillen's fiber lemma, that Z is n-3 connected if and only if Ln is n-3 connected. But Ln, this was the spine of outer space, and we saw in Kai-Uwe's talk this is a contractible space. So a corollary of the high connectivity of this fiber is that Z is n-3 connected. And Z was the same as we saw in the first lemma as this boundary at infinity, which is also the same as the complex of free factor systems. So what we get from this is that this complex of free factor systems is actually n-3 connected. And okay, I didn't write this down here, but one can do the same thing. Everything here restricts also to something on the poset of only those points in the boundary where there's only one non-trivial vertex group. And by the exact same arguments, one also gets, yeah, it's not strictly speaking corollary what I wrote here, but by the exact arguments, one also gets that Fs1n is n-3 connected. So Fn, that's the same as Fs1n is n-3 connected. And now I'm already over time, but let me maybe just wrap up a bit what we did, and then I'll finish. And maybe let me just go back to the board over there. So I wanted to fill in these question marks over here. And I think I didn't completely, I already knew in advance that I couldn't do it as good in the other cases above, but here's what I did. I showed you that for these boundaries, there we have basically two candidates, namely one was this complex, the free factor complex. For the free factor complex, we already knew in advance that it's a complex of dimension n-2. The argument over there showed us that it's n-3 connected. So in particular, it's a wedge of n-2 spheres. For the odd Fn version of it, this was already known, and Jeremy mentioned that. For the out of n version, where we talk about conjugacy classes, this is then the result of Radhika and myself. if you want. But then the problem is this complex here, we already saw there, it doesn't describe all of the boundary. It only gives us those points in the boundary where we have one vertex group with that is non-trivial. Closer to the boundary seems to be this thing, complex of three factor systems. I show what the argument there yields that this is also n-3 connected. And actually one can, if one works a bit harder, one can show that it's actually n-2 connected. Yeah. Yep. Similar argument, one needs to work a bit more with the fibers. One can show that this is n-2 connected, this complex. So in particular, those two are not homotopy equivalent. The problem is this is a complex of dimension 2n-3. So a priori, just knowing that it's n-2 connected doesn't tell us, well, it definitely doesn't tell us that it's a wedge of spheres. So what exactly this looks like is something that I don't know, but I would think would be interesting to know. So Jeremy already mentioned it yesterday. It would be interesting to know whether the homology of this complex, for example, is concentrated in dimension n-1. Actually, I don't even know one non-trivial, one homology class that I can show to be non-trivial in dimension n-1. I can show you a candidate maybe afterwards, but I don't know how to show that it's non-trivial. So reducing the dimension would be interesting. Showing that that actually the homology in this degree is non-trivial would be interesting. And of course, this is a disadvantage of this with the situation above. It was already mentioned in the talks before. The connection of this with the dualizing module is a priori not clear at all. Yeah, because well, here we had the relations of the boundary with the dualizing module because the spaces were manifolds and we had basically Poincaré duality. We don't have that over here, so that's still one step earlier somehow. Yeah, we're getting some complex in the boundary that are highly connected, but it is a priori also not clear how they relate to the dualizing module. That's also something that would be interesting, I guess. Oh yeah, and I did everything here in the description, just a short word with graphs, whereas Jeremy talked about three manifolds, but this is all, I mean, there's a, one can translate all the things into one another, yeah? So the things here that appear here also have an exact correspondence in the three manifold world that Jeremy mentioned. It's just a point of exposition, what one wants to use. Yeah, and that's all, thanks.
Thank you, Benjamin. So are there maybe questions on Zoom? I ask first again. It's always, yes, Kai-Uwe.
So,
oh wait, I'm gonna make us mute again while you talk, so it's easier for you.
Thank you. Is there an interpretation of the three factor complex and the three factor systems thingy in terms of this three manifold and sphere systems picture? So how would I have to picture it there?
Can anyone hear me again? Okay. Yes, so the translation then would probably be via the boundaries instead of the three factors. Maybe I'll change the camera again to the board over here. So a better way would probably to understand what these posetsets, these are sub-posetsets of the free splitting complex. I said the free splitting complex is a complex of, well, of free splitting, so of marked graphs of groups if you want. But you can equivalently also describe it as the complex of sphere systems, where you take exactly the manifold that Jeremy talked about yesterday. 0 marked points in here because we're talking about out, so we don't have a base point and not more definitely. Then you need to translate between free splitting complex and these sphere systems. The translation is you take your manifold for every embedded sphere, and okay, and a sphere system in your manifold gives you an associated structure of a graph of groups by doing the following. Take the manifold, take the spheres and cut the manifold open along these spheres. Then you get one vertex for every connected component of the complement. The vertex group of this vertex is the fundamental group of this connected component. And you get one edge for every sphere. Sphere passes, well, if you go through a sphere, you get from one connected component to another. So that gives you the translation into that assigns to every such a sphere system in a three-manifold and associated graph of groups. So if one goes through the translations, then this complex of all of the boundary is given by all sphere systems in this manifold Mn, such that there is at least one connected component with non-trivial fundamental group. And here you get exactly one connected component with non-trivial fundamental group. This is exactly the translation.
All right, is there another question? Natalie.
You said at some point that maybe the Fn rather than the FFN had maybe something more to do with the boundary of the reduced outer space. Is that the case or not the case?
Yeah, I didn't. Yeah. Maybe I wasn't brave enough to say that it's the free factor complex that has something to do with the boundary here, but let me. Okay. Yeah. No, that's a point that. So let's go to really rank 2. Outer space in rank 2 and the more global picture is somehow, well, you can depict it as a tessellation of the plane in terms of the fairy graph like this. Yeah. This is exactly, and that's the point. This is reduced outer space. Yeah, you have this here, you have roses over here, you have at the points at infinity those. Okay, and so on. What you see is that, so I said the free factor complex. Okay, and then you get these in a slightly different color. For unreduced outer space, you also get at every point such an additional triangle. Sorry, at every point, at every edge corresponding to a rose, you get such a triangle. Now, this boundary Fs1 infinity are those points. This is the free factor complex. And this in rank 2 is also the boundary of reduced outer space, if you want. Whereas already in rank 2, I put the infinity wrong. Okay, but that doesn't matter. Already at 1, you need to this thing to describe the you get these additional. Oh, sorry, these additional. Didn't draw the correct ones, right? For every green thing, so every green thing here is also in the boundary. This is not in the boundary. The green things are in the boundary as well. So here, the unreduced outer space is also the boundaries one higher connected. Here it is actually a wedge of spheres. Yeah, maybe that's also something I should say. Yeah, in rank 2, it is actually true that the complex of free factor system is a wedge of n-1 spheres. But so, and here it would be exactly the boundary. The free factor complex would be exactly the boundary of unreduced outer space. But I am not sure whether this would be true for higher rank. I would suspect not. I mean, a priori, it's definitely not the case. Whether it's homotopy equivalent, I don't know. There is definitely no chance of the boundary of unreduced outer space being the free factor complex there because the connectivity properties differ. For reduced outer space, we only know, I mean, the same argument shows that for reduced outer space, the boundary is n-3 connected, but we cannot update to n-1 connectivity as we did for unreduced outer space. So there a priori, it could be the free factor complex, but I don't see any reason why it should be.
So I believe Kai-Uwe has one more question. So let me mute.
I have a comment and not a question following up on the answer to my previous one, namely that this is sphere systems where at least one complementary component has non-trivial fundamental group. So Karen, Karen has worked out the boundary of dual space. And she tells me that the boundary of dual space is homotopy equivalent to sphere systems with at least one non-trivial complementary component. But of course, since we're working in reduced outer space, you also want the complement to be connected. So that's just something that I can relate.
So I'll just write down, right, this is maybe also something I should have mentioned in this language here. The boundary of dual space is, okay, also according to Karen, homotopy equivalent to boundary of reduced. So now I take the free splittings where I don't allow any separating edges minus the spine of reduced outer space, which is exactly the same that you were saying in terms of sphere systems. Yeah. Yeah, right. Sorry, I should have mentioned that as well, I guess. But, yeah.
Okay, so let's thank Benjamin again. Thank you.